The video for 8.7, which discusses equations in quadratic form, will be broken down into two parts. The first part will deal with real solutions to these equations, and the second part will deal with complex solutions. So, before we begin, we need to remember what a quadratic equation is and what it means for something to be in quadratic form. If you recall, a quadratic equation, not the quadratic formula, but a quadratic equation is an equation with an x squared or a variable to either a squared or an even power. And traditionally we write this in the form y is equal to ax squared plus bx plus c. Now, most people think of this as the traditional form, and we'll look at some examples of that. But this can also be, for instance, you can have the x term here actually be something like y squared or a squared or b squared or whatever you want to use as your variable. In that case, as long as you have this, whatever your variable is here, squared here or double the exponent in this term, then you can end up with quadratic form. So let's look at some examples. All of the examples we have listed here are in quadratic form. Notice with example 10, we've got an x to the fourth and an x squared. Again, the 4 is double the 2, so that's fine. It's in quadratic form. Same thing down here, x to the negative fourth and negative 2. Negative 4 is double negative 2. We've got 4 and 2. Down here in example 12, we've got negative 2 and negative 1 here in example 13. And if you look at example 14, we can also have fractional exponent, which we talked about in the second section in chapter 8. And notice that 2/3 is double 1/3, so this is still in quadratic form. So let's go through and actually solve these. We're not going to use the quadratic formula. You could, but you've got to be careful as to what you use as what you're solving for. In this case, we're just going to go through and try to factor first. So, for instance, if we have this x to the fourth minus 11x squared plus 18, again, we can only factor when things are set equal to 0, not when they are set equal to anything else, because we have to use what's called the zero products rule, meaning two things that are multiplied together, and one of them is 0. So in this case, if we were to factor, we would end up with x squared and x squared, which is why we need this term to be double that of the other. We'll get x squared times x squared is x to the fourth. And then when we do our inner and outer terms, we will end up with just the x squared that's in the middle. So now we need to think of factors that multiply to be 18 and subtract to be 11. Take a second, think about it. You should have found negative 9 and negative 2. Because when you would multiply those together, you would get positive 18, and negative 9 minus 2 would be negative 11 for the middle. Now, since these terms are squared, we need to take another step and say, okay, do any of these terms factor further? And yes, the x squared minus 9 does factor. It is a difference of perfect squares, so it factors to be x plus 3, x minus 3, and we are left with the x squared minus 2. That does factor, but not into perfect squares. So at this point, we take each one of the factors here and set them equal to 0. So we take each one of the factors here and set them equal to 0. So we're going to say, okay, x plus 3 needs to equal 0. Again, this is the zero products rule, meaning that each part of the multiplication is going to give us 0. We've got x minus 3 equals 0. And we have x squared minus 2 equals 0. Now, in this case, we just subtract the 3 over. We get x equals negative 3. In the second one, we add the 3 over. We get x equals positive 3. And for this third one, we're going to have to do two steps. We'll add the 2 over, so we have x squared is equal to 2. And then we would take the square root of both sides. We have to be very careful here because x squared terms always give us two values. So we need to remember that we need to take the positive and negative square root of 2, not just the square root of 2. We need to get both of those answers, positive and negative. So when all is said and done, x is equal to plus or minus 3 or plus or minus the square root of 2. For the next example, it's going to be very similar. The only difference here is that we've got the negative exponents. But again, since the negative 4 is double the negative 2, we're okay. In this case, we're going to end up with an x to the negative 2 and an x to the negative 2. Again, we're splitting that in half. And now we need to find factors of 36 that subtract to be 13. In this case, it's going to be minus 9 and minus 4. And that actually works out nice because, again, we've got the difference of perfect squares, but now in both terms. So we get x to the minus 1. Again, we have to split that in half. Minus 3 and x to the minus 1 plus 3. Down here, we get x to the minus 1 plus 2, x to the minus 1 minus 2. Again, this is all equal to 0. So if we set each of these terms equal to 0, the x to the negative 1 minus 3 equals 0. Let's look at that one first. We'll add the 3 to the other side. And in this step, I'm actually going to rewrite this. Instead of the negative exponent, I'm going to write it as a fraction. And like I said, there's nothing wrong with negative exponents. They're fine. It's just a lot easier to solve equations with fractions than it is with negative exponents. So I'm going to rewrite this as 1 over x, and I'm going to add that 3 to the other side. So we have 1 over x is equal to 3. Now, in this case, we can multiply that x over, so we have 1 is equal to 3x, and then we divide by 3. So x is equal to 1/3. So that is what we end up with in this case. If you can kind of extrapolate from that, you're going to get that the x to the negative 1 plus 3 is going to give us an x to the negative 1/3, because we end up with a 1 over x is equal to negative 3. So x would be negative 1/3. Again, similar process, or the exact same process as we had done before. And if we look at these two terms, the plus and minus, so x to the negative 1 plus 2 equals 0 is going to give us 1 over x is equal to negative 2. Again, if you multiply the x over, you get 1 is equal to negative 2x, and then you divide by the negative 2 to get x is equal to negative 1/2. If you look at x to the negative 1 minus 2 equals 0, you're going to end up with x equals positive 1/2. So all of our answers here, this comes out to be that x is equal to plus or minus 1/3 and plus or minus 1/2. Now, as I mentioned before, these don't necessarily have to be just x's. We can also deal with expressions, more involved terms, as long as they're the same thing. And again, you can kind of think of these as your base. So in this case, you have 2x minus 5 to the 4th and 2x minus 5 squared. So that 2x minus 5 is really your base. Now, some people choose instead here, since these two things are the same, to plug in a different variable. So I'm just going to do this to show you an example, because this might be a technique you would use later on in Tech Math 4 for other things. I am going to first say let a equal 2x minus 5. If I do that, I can rewrite this equation as a to the 4th minus a squared equals 0. So take a second, make sure that that makes sense. We just substituted in a instead of 2x minus 5. And then I can factor this. We don't necessarily have to factor it into the two terms like we did before, because in this case we don't have the constant term. What we can do is factor out the like term, which in this case is a squared, and we'd be left with an a squared minus 1 is equal to 0. And again, from that can factor one more time down to be a plus 1, a minus 1. So now we have three terms. We have a squared is equal to 0. We have a plus 1 and a minus 1 are equal to 0. So if a squared is equal to 0, then a is equal to 0. And if we plug back in, because what we're really solving for is x, then we have 2x minus 5 is equal to 0. So we add that 5 over to the other side and divide by 2 to get that x is equal to 5/2. So that's one of our solutions. Next, we look at the a plus 1. So a plus 1 is equal to 0. That means that a is equal to -1. Again, we substitute in what a was. 2x minus 5 is equal to -1. We would add that 5 over, so 2x is equal to 4, and divide by 2, so x is equal to 2. And for our third answer, I want you to pause the video now and see if you can find the third value. When going through and solving this one, you should have found that x is equal to 3. So we've got our 3 solutions here. X equals 5/2, which is actually what we call a multiplicity 2, meaning it has a double root there because of the a squared. And x equals 2 and an x equals 3. So we've got a few more examples here. We're going to do that same process here on example 13. I want you to pause the video here. We're going to kind of follow a combination of examples 11 and 12 here. So 11 by the fact that we have negative exponents, and 12 by the fact that we're going to want to substitute in. I want you to pause and see if you can do this example on your own. So for this example, you should have gotten that x was equal to -4/3 and that x was equal to -6/5. You need to take it a second, pause the video, and look at the work for this one. Please do so now. I'm going to move on to these last 2 examples that are going to have real solutions. And again, like I said, in this case, we still have that 2/3 is double 1/3, so our exponent in the first term is double that in the second term. And so all we need to do is we need to split this to be x to the 1/3 and x to the 1/3. Very similar to what we've done before. Now we need to find factors of -12 and add to be -1. In that case, it's pretty straightforward, -4 and +3. In this case, we don't have any more squareds left, so we're not going to be able to factor any further. We're just going to be able to set each one of these terms equal to 0. So, for instance, this first one, I'm going to have x to the 1/3 minus 4 equal to 0. So I'll add that 4 to the other side. And how do we get rid of a 1/3 power? Think about this for a second. We did this in section 8.2. The way to get rid of a 1/3 power is to cube both sides, because then that 3 times that 1/3 would give you an exponent of 1. So if you plug that in, you end up finding that x is equal to 64. So that's one of our solutions. If we look at the second part, x to the 1/3 plus 3 is equal to 0. Then we subtract that 3 to the other side. And again, we say, okay, we need to cube both sides. So in this case, we end up with x being -27. So if you remember from the previous section, we said that whenever we're going through and doing this, and we need to raise things to a power, that it is possible that we've introduced an extraneous solution. So we want to go back through and check both of these just to make sure. If you plug in 64, you get 64 to the 2/3 minus 64 to the 1/3 minus 12. And we want to see if that equals 0. Well, let's think about it. 64 to the 2/3. That means we're taking the cube root of 64, which is 4, and then squaring that, which is 16. So we get 16. 64 to the 1/3 is 4. Minus 12, that indeed is 0. So we're good. If we check -27, we would find out that it also does work. Okay, we have one final example here. We're kind of pulling together everything we've learned so far. And so if you see here, we've got these roots. Well, we know that we can always rewrite roots with fractional exponents. So in this case, we're going to rewrite this as x to the 1/4 plus 2x to the 1/2 equals 3. Now we have to think about this for a second. Which one of those exponents is double the other? Well, the 1/2 is actually double the 1/4, so these are not written in the correct order. It's also equal to 3, so we need to make sure that we set it equal to 0 by subtracting that 3 over to the other side. So if we rewrite, this is really 2x to the 1/2 plus x to the 1/4 minus 3 is equal to 0. Now we say, okay, this isn't too bad. The only thing that we have to be careful of here is that now we're going to have a 2x to the 1/4. Again, we're taking half of the exponent. A half of a half is a quarter, and that's also our middle term here. And we're going to have an x to the 1/4. We were lucky that our coefficient was a 2. The only options that we have to multiply together are 2 and 1. Now we just need to figure out where the factors of -3 go. And in this case, it actually works out. You're going to want a 3 and a 1. And if you want this term to be positive here, you want the 3 to be positive and the 1 to be negative. Because if you multiply the 3x to the 1/4 and the -2x to the 1/4, then you end up with a positive 1 in the middle here. So, again, we set each one of these terms equal to 0. So we have a 2x to the 1/4 plus 3 is equal to 0. Subtract the 3 over, divide by 2, and the last step to get rid of the 4th root is to raise both sides to the 4th power. And in this case, we end up with x being equal to a positive 81/16 if you raise both of those, numerator and denominator, to the 4th power. I want you to pause the video here and find the final solution to this equation. And check both to make sure that there are no extraneous roots. So if you went through this last one just equals 1, it's not too bad. The thing that you should have found that when you go through and check is that 81/16 does not work. It comes out to be 6 when you plug it into the radicals, which does not equal 3. So our only solution in this case is 1. So this is the end of this video. The next video will look at how we deal with complex or imaginary roots to quadratic equations.